Register is a one-word storage device. While discussing the flip-flops, we learned a single flip-flop can store a bit. Once we are talking, a register is a one-word storage device. A word in general may be group of n bits. So that to store group of n bits, it required to use group of n flip-flops. So basically, we are talking the register is one word storage device. For any storage device, we need to have the facility to write the data into the device, and we need to have the facility to read the data from the device. So writing the data into the device is possible maybe only one bit at a time. If at all we are writing only one bit at a time into the device, such operation we suppose to name as serial input operation. It may be possible to write all the bits simultaneously into the device. Such operation we must name as the parallel input operation. As similar to this writing operation, when we are retrieving the data, that is when we are reading the data from the device, it is possible to read the data from the device maybe only one bit at a time. If at all we are reading only one bit at a time from the device, such operation we suppose name as serial output operation. If at all we are reading all the bits simultaneously from the device, such operation we suppose name as a parallel output operation. Based on these various writing and reading operations, we are having a possibility of the registers with the facility of serial input, serial output operation, serial input, parallel output operation, parallel input, serial output operation, parallel input, parallel output operation. A part of this, we are having a possibility the data which is available in the register to shift the data to the right, we are having a facility. So if at all we are having possibility to shift the data left to right, then we are naming it is a right shift facility. Or we may be having a facility to shift the data right to left. If the data is possible to shift in the register from right to left, then we are naming the facility of the register is a left shift facility. So in general, we are having a possibility of the registers with these various facilities. If at all in the given register we are having all these facilities, then such a register we are naming as universal register. In fact, in the given register, if at all we are having at least this right shift facility or left shift facility, then we must name the register as shift register. As and when the register is having all these facilities, you can name as universal register, or if you want, we can name even as universal shift register. Let us try now few of the register circuits with few of these facilities. So let us try for a 4-bit shift register. Once we are talking, we want to develop a 4-bit shift register, we need to use 4 flip-flops because we are talking a register which is supposed to be the size of the 4-bit storage. Once it is storing the 4 bits, then definitely we are in need of 4 flip-flops. In general, if at all we are looking to realize the register, we are having a possibility to use SR flip-flops, JK flip-flops, D flip-flops. But directly it is not possible to use T flip-flops. We are unable to use the T flip-flops directly. Why it is not possible for us to use the T flip-flops directly? While discussing the circuit, let's try to identify. Let us try here the 4-bit register by using JK flip-flops. Consider this is the register which is going to store the most significant bit of 4-bit data. Suppose 4-bit data, the bits of B3, B2, B1, B0. Then this flip-flop supposed to store the bit B3 and so on. This flip-flop supposed to store the bit B0, so that it is the flip-flop which is going to store the least significant bit. Based on this, let us name the flip-flops. This let us name flip-flop 0. This as a flip-flop 1. This as flip-flop 2. And this is flip-flop 3. And we are naming, based on these names, the terminal names of each flip-flop. All these flip-flop clear terminals are shorted. And similarly, all these flip-flop preset terminals also shorted. The flip-flop 0 inputs are coming from the flip-flop 1 outputs. So flip-flop 1 output Q1 and Q1 bar are the inputs of the flip-flop 0, J0, K0 respectively. Similarly, the flip-flop 2 outputs are the flip-flop 1 inputs. Flip-flop 3 outputs are the flip-flop 2 inputs. Between the J and K terminal of flip-flop 3, let us use a NOT gate, and this input let us name as the serial input. Consider the flip-flops with the negative edge triggered clock. Clock to all these flip-flops is common, so external clock is coming directly to all these flip-flops. So we are looking basically in this circuit, except this MSB flip-flop. For the remaining flip-flops, we are looking flip-flop I inputs are coming from the flip-flop I plus 1 output, and MSB flip-flop is having the input from the external source. This external terminal we are naming as serial input. It is a connection, or these are the connections what we are looking in the circuit. And also we are having a possibility to recognize easily between the J and K terminals of any flip-flop. We'll be having always the complementary input. So while looking to the complementary inputs between the J and K terminals, it is possible to recognize all these JK flip-flops are giving effectively the operation as the D flip-flop operation. We are looking, all these flip-flops are basically are having the D flip-flop operation. From the truth tables, the D flip-flop, we know what is the D input we are having. It is coming as the output as and when we are applying the clock signal. So with this knowledge, it is easily possible for us to understand the operation easily. Before going to apply the clock signal, or before going to apply the serial data to the circuit, before going to use the circuit, basically we want to clear all the flip-flops first. It means we want to read all these flip-flop outputs, this is Q3, Q2, Q1, Q0, all these flip-flop outputs we want to read as 0, 0, 0. So to read all the flip-flop outputs to be 0, 0, 0, it required for us to keep the clear 0 and preset 1. After keeping clear 0, preset 1, we are going to read all the flip-flop outputs are 0. Later we want to apply the clock signal. While applying the clock signal, we want to write the data into the register. So to apply the clock signal, the clear and preset both must be connected to 1. To apply the clock signal, clear and preset both must be connected to 1. So that to apply the clock signal, we are applying here a clear 1, preset 1. It is the required initial setup for this serial input operation. Later, let us consider we want to load this number into the register. We want to write this data 1011 into this register. Initially, we want to keep the serial input terminal bit B0 value. Bit B0, as per the sample, it is 1. Now, if you apply the clock signal, we know, as I already mentioned, before applying the clock signal, what is the D input we are having, it is transferred to the output. So before applying the clock signal, now at this instant, if at all you are looking, flip-flop 3 input is B0, that is 1. Flip-flop 2 output is the flip-flop 3 output was 0. Flip-flop 1 output is the flip-flop 2 output. So flip-flop 2 output again 0. Flip-flop 0 input is flip-flop 1 output, again it is 0. So that flip-flop 1 data is transferred to the flip-flop 0. Flip-flop 2 data is transferred to the flip-flop 1. Flip-flop 3 data is transferred to the flip-flop 2. And external input is entering into the flip-flop 3. Hence, based on this, as and when we are applying the clock signal, bits B0 is coming to Q3. And Q3 bit is coming to Q2. Q2 bit is coming to Q1. Q1 bit is coming to Q0. So, it is the content in the register after first clock pulse. Before applying the second clock pulse, at the serial input, we want to keep the bit B1. As per our sample number, the B1 bit is 0. So while applying the clock signal, B1 bit is coming to flip-flop 3. Flip-flop 3 bit is coming to or transferred to flip-flop 2. Flip-flop 2 bit is transferred to the flip-flop 1. Flip-flop 1 bit is transferred to the flip-flop 0. So it is the content of the register after second clock pulse. Now before third clock pulse, we want to keep the bit B2 at the serial input. The bit B2, as per our sample number, it is 1. Now while applying the clock signal, bit B2 is coming to Q3. Q3 bit is transferred to the Q2. Q2 bit is transferred to the Q1. Q1 bit is transferred to the Q0. So it is the content of the register after third clock pulse. Now, before applying the fourth clock signal, bit B4 we are keeping at the serial input. Bit B3 we are keeping at the serial input. As per sample number, it is 1. Now, while applying the clock signal, B3 is coming to Q3. Q3 bit is coming to Q2. Q2 bit is transferred to the Q1. Q1 bit is transferred to the Q0. So that after fourth clock pulse, we are looking the flip-flop 0 bit B0 is available. In the flip-flop 1 bit B1 is available. In the flip-flop 2 bit B2 is available. In the flip-flop 3 bit B3 is available. So for this serial input operation, in this 4-bit case, we are in need to use 4 clock pulses. So based on this, if at all we are looking in general, for this serial input operation, for 4-bit case, we are using 4 clock pulses. Hence, for n-bit case, we are in need of n number of clock pulses. After writing this data into the register, if we want to read all the bits simultaneously, we are having a possibility to read all the bits simultaneously. After this fourth clock pulse, we are looking bit B0 here, bit B1 from the flip-flop 1, bit B2 from flip-flop 2, bit B3 from the flip-flop 3. and we are having a possibility to access all these 4 bits simultaneously. But all we are accessing all the 4 bits simultaneously, this operation we suppose to name as parallel output operation. So that in the circuit, we are looking to the facility of serial input parallel output operation. And we are looking here, after writing this data into the register, for parallel output operation, we are not using any clock signal. So that even for n-bit case is same, we are not in need to use any clock pulse for parallel output operation. Once we are writing the data in the register, we are having a possibility to access all the bits simultaneously without using any clock signal, so that for parallel output operation we are not in need to use any clock pulse. And we want to read the data only 1 bit at a time from this register. One of the way it is possible using the flip-flop 0 output as a serial output terminal. So while using the flip-flop 0 output as serial output terminal, without applying any clock signal, we are having a possibility to read bit B0. So bit B0 we are reading as 1. Now, after reading the bit B0, the next bit we want to read from the register is bit B1. So for reading the bit B1, it required to transfer the bit B1 to the flip-flop 0. Hence, while keeping serial input 0, we need to apply a clock signal. While keeping serial input 0, if we apply the clock signal, we are looking the B1 bit is transferred to the flip-flop 0, B2 bit is coming to the flip-flop 1, and B3 is coming to flip-flop 2, and of course 0 is present in the flip-flop 3. So after this first clock pulse, we are able to read from the serial output terminal bit B1, it is 0. Similarly, after reading the bit B1, next bit we are supposed to read, it is B2. To read the bit B2, it required to transfer the bit B2 to the flip-flop 0. Hence, it required for us to apply one more clock. So, as and when we are applying the clock pulse, then only the data in the register is shifting 1 bit to the right. So, while keeping serial input 0, if you apply one more clock pulse, we are going to look B2 in the flip-flop 0, so that from the serial output terminal, we are having access to read the bit B2. After reading the bit B2, to read the bit B3, we are applying one more clock pulse. So with this, we are going to look bit B3 is available in the flip-flop 0, so that from the serial output terminal, we are able to access bit B3. So we are looking, after 3 clock pulses, all the bits are available from the serial output terminal. And we are looking here, we are reading only 1 bit at a time from the register. This operation we suppose to name as the serial output operation. So that as it is in this circuit, we are able to recognize the circuit is having the facility of serial input, serial output operation. For serial output operation, for this 4-bit case, we are in need to use 3 clock pulses. Hence, for n-bit case, we are in need to use n-1 clock pulses. For serial input purpose, n number of clock pulses. Serial output purpose, we are in need to use n-1 number of clock pulses for n-bit case, while looking to the circuit with a serial input, serial output operation. For serial input operation, on this content, whatever the table we develop, this table content, we are having a possibility to look as a figure. If at all this table content of serial input operation, this is for serial input, this is serial output. So this table content, while reading as a figure for serial input operation, that figure we suppose to name as timing diagram. Let's try to develop the timing diagram. So we consider the flip-flops, the negative triggered clock. Now with respect to this clock, if at all we are giving a figure for this table content, it is possible to look here. Flip-flop 3 is initially 0. Of course, all the flip-flops are initially 0. Q3 waveform, if at all we are looking, initially 0. After first clock pulse, it is getting 1. They're talking after first clock pulse. The reason is very simple, because of negative triggered. So that after applying the first clock pulse, it is getting 1. And after second clock pulse, it is 0. After third clock pulse, it is 1. After fourth clock pulse also, it is 1. Similarly, if you look to the Q2, initially 0 until to second clock pulse. After second clock pulse, it is getting 1. At third clock pulse, it is 0. After fourth clock pulse, it is getting 1. And similarly, if you look to the Q1, initially it is 0 until to third clock pulse. At third clock pulse, it is 1. After fourth clock pulse, it is 0. We come to the flip-flop 0. Initially 0 until to fourth clock pulse. After fourth clock pulse, it is 1. So that after 4 clock pulses, the content in the register we are able to look as 1101. And this figure we are naming as the timing diagram. In the sequential circuits, the timing diagram is one of the important concepts. Generally, we will be having questions based on the timing diagram on the sequential circuits. We consider the serial input data as 1101, so that it's the timing diagram for this serial input operation in this register. If at all, the flip-flops, instead of having the negative triggered clock, they are having the positive triggered clock. Then what changes we are looking the timing diagram? If you see the transitions, what we are looking here, these are transitions. Instead of at falling edge of the clock, we need to read at the rising edge of the clock, so that the waveforms will shift a little left by this pulse width amount. Or instead of this 1101, if at all the content of the register is, say for example 1011 with the same negative edge triggered, then definitely the timing diagram is not coming to be same. The timing diagram will differ. So that in this register, for this serial input operation, whenever we are developing a timing diagram, the timing diagram is going to differ based on the trigger as well as based on the data what we are going to write into the register. So anyway, this timing diagram is one of the important concepts in general for any sequential circuit. In the beginning of this topic, we were talking for realizing registers, we are unable to use directly these T flip-flops. Why it is so? Let us try to discuss now. In this register circuit, we are having the usage of the JK flip-flops. Based on the connections, we are able to recognize at any moment the J and K inputs are not having a chance to be 1-1 inputs. Hence, we are having a possibility to replace all these JK flip-flops even with the SR flip-flops. Whether we are using SR flip-flops or JK flip-flops, based on these connections, effective operation of all these flip-flops is D flip-flops. So that we are having a possibility to use even the D flip-flops. But coming to the T flip-flop, we know well, T flip-flop directly not possible to use. The reason, if you speak, what are the flip-flops we want to use to build the register, those flip-flops effective operation we want to have as a D flip-flop. Directly T flip-flop we can't use as a D flip-flop. Of course, I am using this prefix word directly, but we know from the flip-flop conversion, any flip-flop can be converted to any other flip-flop. The extra additional hardware, if at all we are converting T flip-flop to D, and then if we want to use, no issue. But we are talking directly we are unable to use. So any flip-flop, what is the flip-flop we want to use in the register implementation, those flip-flops effective operation we are expecting to be with the D flip-flop operation. Hence, we are unable to use the T flip-flops directly to realize the registers. And in this register circuit, we are looking to the operation of the right shift. We are having the operation of this right shift. So this register, based on this only, we are able to name it is a shift register. As it is in the circuit, of course, we are not looking the left shift operation. And of course, parallel input, serial output, parallel input, parallel output operation also we are not having. Let us develop separate circuits when for this parallel input, serial output, parallel input, parallel output. Here in this register, between the flip-flop 2 and flip-flop 3, we are using a multiplexer. Between the flip-flop 1 and flip-flop 2, also a multiplexer. Between the flip-flop 0 and flip-flop 1, also we are using a multiplexer. And of course, all these multiplexers are the size of 2 by 1. Now, let's look the operation of this circuit. By using this clear terminal, we are clearing all the flip-flops first. After clearing all the flip-flops, we are keeping clear 1. So that we are in a position now to apply the clock signal. While keeping M is 0. M is basically coming to be the select input of all these 3 multiplexers. Whenever M is 0, from these multiplexers, the line 0 is going to be selected. Line 0 of this multiplexer is a parallel input to line 0 of this multiplexer is a parallel input 1. Line 0 of this multiplexer is a parallel input 0. So that from these multiplexers, the output, if at all we are looking, here we are going to look parallel input 2, here a parallel input 1, here the parallel input 0. So at this instant, if at all we are applying the clock signal, the parallel input 3, if at all it is a bit B3, and the parallel input 2 is a bit B2, parallel input 1 is a bit B1, parallel input 0 is a bit B0, then B0 is the input to the flip-flop 0, B1 is the input to the flip-flop 1, B2 is the input to the flip-flop 2, B3 is the input of the flip-flop 3. So that as and when we are applying the clock signal, all the bits are entering into the register simultaneously. So all the bits are entering to the register simultaneously, hence this operation we suppose name as the parallel input operation. For this parallel input operation, we are in need to use 1 clock pulse. For this parallel input operation, we are in need to use 1 clock pulse. Whether it is a 4-bit case or 5-bit case or in general with size of n bits, we are in need of only 1 clock pulse. For parallel input operation purpose, we are in need to use only 1 clock pulse. After writing this data into the register, if you want to read all the bits simultaneously from the register, we are having a possibility to access all the 4 flip-flop outputs directly. Once we are able to access all the bits simultaneously, this operation, of course, we suppose name as the parallel output operation. So that the circuit is having the facility of this parallel input, parallel output operation. So as usual, for parallel output operation, we are not in need to use any clock pulse. And we want to read only 1 bit at a time from the register. After writing the data into the register in the parallel form, we want to read only 1 bit at a time from the register. Then for that purpose, we are having a possibility to use a flip-flop 0 output as a serial output terminal. And here we need to keep M value as 1. For serial output operation purpose, we need to keep M is 1, and we need to keep the parallel input 3 as 0. And of course, we are looking M is 0 is the case for parallel input operation. For serial output operation, M must be 1 and the parallel input 3 must be 0. Whenever M is 1, from these multiplexers, I1 is selected. So that without any clock pulse, bit B0 is available. As and when we are applying the clock signal, the flip-flop 1 data is transferred to the flip-flop 0 because I1 is the input to the multiplexer which is coming from the flip-flop 1 output. So effectively the output of the multiplexer is bit B1. So B1 is the input of flip-flop 0 means after first clock pulse B1 is possible to read and so on. So that we are looking here the circuit to the facility of serial output. So the circuit we can say now is the facility of the parallel input serial output operation. For 4-bit case, for serial output operation, of course, we are in need to use 3 clock pulses. For n-bit case, we are in need of n-1 clock pulses. So we are looking here the circuit to the facility of the parallel input, parallel output as well as parallel input serial output operation. And of course, this register we are having a possibility to use even for serial input, serial output, serial input, parallel output operation. For serial input operation purpose, we are in need to use M as 1. And anyway, serial output M is 1. For serial input, serial output operation, M is going to be always 1. Once we are writing data, parallel data we can access without applying any clock signal. So that as it is the circuit, we are looking at the facility of the serial input, serial output, serial input, parallel output, parallel input, serial output, parallel inputs, parallel output, and also it is having the facility of the right shift. Of course, it is not having the facility of the left shift, so that we should not name as a universal shift register, but we can name in general it is a shift register, so that it is a 4-bit shift register with all these facilities except this left shift facility. And from this we are able to recognize from all this discussion, for serial input, serial output operation, total number of clock pulses if at all we are looking, for a serial input for n-bit case if at all we are talking, for serial input n, for serial output n minus 1. So that for serial input, serial output 2n minus 1 number of clock pulses required. And for serial input, parallel output operation, we are in need of only n number of clock pulses. And for parallel input, serial output operation, we are in need of n number of clock pulses. For parallel input purpose, 1 clock pulse, and serial output purpose n minus 1. So total number of clock pulses n minus 1 plus 1 becomes n. And parallel input, parallel output operation, we are in need of 1 clock pulse. So this is the conclusion, or this is the conclusions what we can speak on these registers. Let's look to the applications of the shift registers. They are having various applications of the shift register. Let's start. It is possible to use to convert the serial data to parallel form. They are having a possibility to use the register to convert the serial data to parallel form with serial input, parallel output operation. So if at all we are having a register of 4-bit, so with this serial input terminal, we are writing the data into the register. If the serial input data is something like this, after 4 clock pulses, all these 4 bits are available from the parallel output terminals. So that we are looking here, the register is converting the serial data to parallel form with this serial input, parallel output operation. It is possible to use to convert the parallel data to serial form. And this conversion, parallel data to serial form, we are able to look with this parallel input, serial output operation. The register, consider it is having the parallel input operation facility. With this parallel input operation facility, we are loading all the bits simultaneously into the register. If all the 4 bits we are loading simultaneously into the register, then while applying the clock signal, we are able to read only 1 bit at a time from the serial output terminal. So in this case, the role of the register is coming to be converting the parallel data to serial form. The third one, it is possible to use as delay circuit. The best way to use the register as a delay circuit is serial input, serial output operation. With the serial input, serial output operation, after writing the data into the register, we are able to read the complete data from the register after applying n-1 number of clock pulses. So for writing purpose, n number of clock pulses, for reading purpose, n-1 number of clock pulses, so that the amount of delay involved will be 2n-1 into the clock repetition time. And of course, it is possible even with the serial input, parallel output, parallel input, serial output also, but the best way to use the register as a delay circuit is the serial input, serial output operation. It is possible to use as divided by 2 circuits. If at all we are looking, the data which is available in the register is 1010. With this 1 bit right shift operation, the data in the register is going to be 0, 1, 0, 1. So initial content is 10, while shifting 1 bit to the right, it is coming to be 5, so that the original data is divided by 2. So that we are able to use the register as divided by 2 circuits. It is possible to use the circuit as multiplier by 2 circuits. So the divided by 2 circuit we are having with right shift operation. We want to use a resistor as a multiplier by 2 circuit. It is possible with the left shift operation. Suppose consider the original content of the register is 0, 1, 0, 1. With 1 bit left shift operation, we are going to look 1, 0, 1, 0. The original content is 5. After left shift, it is coming to be 10. So it is as good as multiplying with 2. So we are having with the right shift facility the divided by 2 circuit operation, with the left shift facility multiplied by 2 circuit. But of course, this division and multiplication is with a restriction. So in the case of division, the restriction is, if at all this LSB bit is 0, it is a true division. If at all LSB bit is 1, it is not a true division. If at all LSB bit is 1, we are going to look, suppose for example 1, 0, 1, 1, then with the right shift it is 5. But we know 1, 0, 1, 1, it is 11, so that we are having an error of 0.5. Hence, we are looking the true division whenever LSB bit in the original data is 0. If at all LSB bit in the original data is 1, we are having an error of 0.5. As similar to this, even in the left shift operation, if in the original data MSB bit is 0, it is a true multiplication. In the original data, if at all MSB bit is 1, say for example MSB bit is 1 instead of 0, then we know that this is coming to be now 13. After left shift, it is coming to be 10. But expected result is 26. But what we are reading is 10. It's wrong. So that we are looking at difference of 16. For 4-bit case, it is a difference of 16. That is to the power of 4. Hence, for n-bit case, it is coming to be to the power of n. Hence, we are having true multiplication with the left shift operation if and only if MSB bit is 0. If at all the MSB bit is 1, the multiplication is with error. Error is to the power of n for n-bit case. The next application is, it is possible to use as a counter. It is possible to use as a counter. We are having a possibility to use the resistor as a counter while connecting Q0 to serial input terminal. We are having possibility to use the resistor as a counter while connecting Q0 bar to serial input terminal. While connecting Q0 to serial input terminal, what is the counter? We are getting this counter, we are naming as ring counter. While connecting Q0 bar to serial input terminal, what is the counter? We are going to get this, we are naming as twisted ring counter or Johnson counter or Mobius counter. In fact, if at all you are looking, what is a counter? Counter is basically a measuring instrument. So in this case, it is measuring clock pulses. We know for any measuring instrument, to measure the quantity, there is an upper limit. Suppose if you take a particular voltmeter, the given voltmeter can measure maximum say 10 volts, 5 volts, 10, 20 volts, 1 volt, etc. So as similar to any other measuring instrument, even coming to this counters also, for measuring quantity, there is an upper limit. If at all the given counter is counting maximum k number of clock pulses, then that counter is named as mod k counter or divided by k counter. If the given counter is counting maximum k number of clock pulses, then it is named as mod k counter or divided by k counter. The standard terminology with respect to any counter. So let us try to estimate now when we are using a given register as a ring counter, what is the mod value? When we are using the register as a Johnson counter, what is the mod value? Let us try to recognize. Let's take again 4-bit case. As we are talking, Q0 is coming as a serial input. Q0 is coming as a serial input of the counter. Suppose we are looking to the initial content in the register is this. In fact, the best way to use the register as a counter is one of the bit of the register must be 1 and the remaining bits must be 0. Why it is the best way, I will discuss little later. Suppose consider we are having the initial content in the register as Q0 is 1 and the remaining bits are 0. Now while connecting Q0 to serial input terminal, it means we want to use as a ring counter. Now we are looking without applying the clock signal, serial input is 1. At this point, if at all we are applying the clock signal, this serial input is coming to Q3. Q3 bit is transferred to the Q2, Q2 bit is transferred to the Q1, Q1 bit is transferred to the Q0. So that after first clock pulse, the content in the register we are looking 1, 0, 0, 0. And before second clock pulse, if we look to the serial input, it is 0 because now Q0 is 0. After second clock pulse, the content in the register is this. Like this, we are supposed to go on, apply the clock pulses until the circuit is back to initial state. So it is not the initial state, so that we are going further clock pulses. So before third clock pulse, serial input, if at all we are looking, it is 0 because Q0 is 0. After third clock pulse, the content in the register, we are going to look like this. So it is not the initial state, we are going further clock pulses. Before fourth clock pulse, serial input is 0. After fourth clock pulse, we are going to look at the content in the register. So that after 4 clock pulses, the circuit is back to initial state. So for this 4-bit case, the circuit is counting 4 clock pulses. Based on this, we are naming it is a mod 4 counter or divided by 4 counter. So 4-bit case, we are having the register as a mod 4 counter or divided by 4 counter. For n-bit case, it is possible to speak, it is possible to use as mod n counter or divided by n counter. N we are using as size of the register. For this table content, if you want to develop the timing diagram, as I said already, the timing diagram is always with respect to clock signal. If you look to the Q3, initially it is 0. After first clock pulse, it is getting 1. After second clock pulse, it is 0. And so on. After fifth clock pulse, again it is getting 1. After sixth clock pulse, it is 0. And so on. If you apply further, after ninth clock pulse, once again it is 1. After 10th clock pulse, it is 0. And so on. It is a Q3 waveform. Of course, we considered the same circuit what we developed as a beginning circuit for serial input, serial output operation. It is a negative edge triggered flip-flops. So that the changes we are trying to look when the clock is falling. If you look to the Q2, initially 0 until to second clock pulse. After second clock pulse, it is 1. At third clock pulse, it is 0. If you apply further, after sixth clock pulse, it is 1. After seventh clock pulse, it is 0. After 10th clock pulse, again 1, and so on. If you look to the Q1, initially it is 0 until to third clock pulse. At third clock pulse, it is 1. After fourth clock pulse, it is coming to 0. We apply further clock pulses. After seventh clock pulse, it is 1. After eighth clock pulse, it is 0, and so on. If you look to the Q0, initially it is 1. After first clock pulse, it is coming to 0. Same 0 will continue until to fourth clock pulse. After fourth clock pulse, it is 1. After fifth clock pulse, it is 0. If you continue further, after eighth clock pulse, again it is getting 1. After ninth clock pulse, it is 0, and so on. So it is a timing diagram what we are looking for this ring counter for 4-bit case with the initial content assuming Q0 is 1 and the remaining 3 bits are 0. From this figure, if at all we are trying to look the repetition time of flip-flop outputs. Assume the clock repetition time is Tc. If at all we are looking to the repetition time of any flip-flop outputs, we are going to look 1, 2, 3, 4. It is coming to be 4 into Tc. If at all we are measuring at any flip-flop output, we are looking to the repetition time as 4 into Tc. So that if at all we are looking to the frequency at any flip-flop output, if we read the frequency at any flip-flop output, it is coming to be 1 upon 4 into Tc. It is nothing but clock frequency by 4. It means if at all we are using a clock of frequency 1 kilohertz, from any flip-flop output we are reading the frequency as 250 hertz. So that the clock frequency is divided by 4. It is the reason why we are naming it is a divided by 4 counter. The standard meaning with respect to in general any counter, as and when we are talking it is a divided by so and so. We are talking a given counter is divided by 12 counter. The meaning is that counter can divide the applied clock signal by a decimal number 12. This is the means of the word divided. We were talking the best way to use the register as a counter is one of the bit of the register must be 1 and the remaining bits must be 0. So why it is so? Let us look with a small example. Consider initial content of the register is 1010. When we are using this register as a ring counter, we need to connect Q0 to serial input terminal. Now, before applying the clock signal, serial input is 0. If you apply the clock signal, the content in the register we are going to look as this. Now, before second clock pulse, serial input is 1 because Q0 is 1. If you apply the clock signal, we are going to look to the data in the register is this. So that we are having the circuit is back to initial state just after 2 clock pulses. Hence, if you want to use a register as a full length ring counter, then definitely this initial content is not so suitable. Hence, we mentioned the best way to use the register as a counter is where the bit of the register must be 1 and the remaining bits must be 0. Now, let us consider the case how we are using the register as a Johnson counter. Consider here also the initial content in the register is Q0 is 1 and the remaining 3 bits are zeros. And now, if you want to use the register as a Johnson counter, that is a twisted ring counter, Q0 bar must be connected as a serial input. While connecting Q0 bar as a serial input terminal without applying the clock signal, if you look to the serial input terminal, having Q0 is 1, Q0 bar is 0. Now, if you apply the clock signal, we are looking the data in the register is this. Now, before second clock pulse, if at all we are looking to serial input, it is 1 because Q0 is 0, Q0 complement is 1. If we apply the clock signal, we are going to look, it is the content. And like this, we are supposed to go on, apply the clock pulses until the circuit is back to initial state. So, before third clock pulse, it is 1. So, after third clock pulse, it is the content. Before fourth clock pulse, it is 1. After fourth clock pulse, it is the content. Before fifth clock pulse, it is 1. After fifth clock pulse, it is the content. Now, before sixth clock pulse, if we look, serial input is 0 because the Q0 is 1. Now, if you apply the clock signal, we are looking, it is the content. Before 7th clock pulse, it is 0. After 7th clock pulse, it is the content. Before 8th clock pulse, it is 0. After 8th clock pulse, it is the content. So that the circuit is back to initial state after 8 clock pulses. So, 4-bit case, it is a mod 8 counter or divided by 8 counter. Based on this, for n-bit case, it must be mod 2n counter are divided by 2n counter. For n-bit case, it is a mod 2n counter or divided by 2n counter. Okay, let's go to the next application. We are having possibility to use the register as sequence / waveform generator. We are having possibility to use the register as a sequence slash waveform generator. If you look how we are using the register as sequence or waveform generator, one of the simplest way we can look how we are using a sequence generator. When we are using the register as a counter, suppose if at all we are reading the output from Q2, for every 8 clock pulses this bit pattern is going to be repeat. It is nothing but the sequence generation. But all we are looking this as a figure, it is a waveform generator. So that we are having a possibility to use the register as a sequence or waveform generator. So these are the few important applications of the shift register. Whatever the registers we discussed till now, in those registers we are looking only right shift operation. We recognize the data was shifting from left to right. So those registers were right shift registers. As I said in the introduction, we are having a possibility to shift the data to the right as well as left shift. If at all we want left shift operation in the register, then data must shift from right to left. If the given register is having both right shift as well as left shift operation, the given register is having both right shift and left shift operation, then that register we suppose to name as bidirectional shift register. Let us look here one of the example of 4-bit bidirectional shift register. So in this 4-bit bidirectional shift register, we are using the D flip-flops. All the flip-flop clear terminals are connected to the common terminal, and of course we are considering the flip-flops are the positive triggered. All the flip-flops are having the common clock from the external source, and we are looking the flip-flop inputs are coming from these 2-level AND/OR circuits. In this 2-level AND/OR circuit, to understand the operation easily, we name few flip-flops with the name of A, A3, A2, A1, A0, and the remaining, not few flip-flops, few AND gates. In this 2-level AND/OR circuit, this few AND gates we named with the names of A, A3, A2, A1, A0. The remaining AND gates of this 2-level circuit, we are using the names B0, B1, B2, B3. Just for our understanding purpose, we named these things. We are going to look how we are having the distinguish. So anyway, for this, in this register, before going to look maybe for right shift operation or maybe for left shift operation, we need to clear all the flip-flops. So clearing operation we are looking while keeping clear 0. And if at all we are having in the register preset also, preset will be connected to 1. But we know few of the flip-flops are having only clear terminals, few of the flip-flops may be having only preset terminals, few of the flip-flops may be having both clear and preset. So it is not the matter, but basically we are going to clear all the flip-flops first. And let us consider here, these flip-flops are having only clear terminals. After clearing all the flip-flops, the clear terminal is connected to 1. Later, for this right shift operation, we need to keep M is equal to 1. While keeping M as 1, it is possible to look, while keeping M is 1, it is possible to look based on the connections. One of the input of AND gate, A3, A2, A1, A0 is 1, whereas one of the input of this AND gate B3, B2, B1, B0 is 0. So that while having one of the input of AND gate B3, B2, B1, B0 is 0, these AND gate outputs are 0 because M complement is the input to the B gates. Hence, B3, B2, B1, B0 outputs are 0. And A3, A2, A1, A0 outputs, basically they are enabled. Now we can speak enabled. And A3 output is a serial left input. And A2 output is a Q3, that is the flip-flop 3 output. And A1 output is Q2, A0 output is Q1. So at this point, if you apply the clock signal, the data is entering into the register, so that we are looking Q3 data is transferred to the flip-flop 2, flip-flop 2 data transferred to flip-flop 1, flip-flop 1 data transferred to flip-flop 0. So that circuit is having now a right shift operation. So with M is 1, we are looking to the right shift operation. Similarly, whenever M is 0, it is going to be reverse. Whenever M is 0, it is possible to speak, I indicate A3, A2, A1, A0 are disabled, B3, B2, B1, B0 are enabled. Now, we can look, B0 output is the flip-flop 0 input, that is serial right input. B1 output is a flip-flop 1 input, B1 output is Q0. So Q0 is coming as the flip-flop 1 input. Similarly, flip-flop 1 input is coming as the flip-flop 2 input, flip-flop 2 input is coming as the flip-flop 3 input. So at this point, if we apply the clock signal, the data we are looking, which is shifting 1 bit to the left as and when we are applying the clock signal, so that the circuit is having the left shift operation. So we are looking here in this circuit, the data is having a chance to shift to the right as well as left. Having both right and left shift operations, we are naming the resistor as bidirectional shift resistor. One other point we need to bother here, by using serial left terminal, if we want to load the resistor 1 bit at a time, then the first bit to be entered will be least significant bit, that is a bit B0, because the bit what we are writing as the first bit, it is supposed to be available after 4 clock pulses in the flip-flop 0. Similarly, by using serial right input terminal, if you want to load the resistor into the resistor, the first bit to be entered in the resistor must be the most significant bit. The bit what we are writing is the first bit, after 4 clock pulses, it must available in the flip-flop 3. The reason the first bit to be entered into the register is the most significant bit. So it is a serial right input, it is a serial left input. It is a serial left input. In this figure, the first bit must be the LSB bit, and in this figure, serial right input, first bit must be the most significant bit. So here we developed this 4-bit bidirectional shift resistor. Based on this knowledge, it is possible to develop a resistor of any other size of 5-bit or 6-bit or 8-bit or 3-bit. So it's a general description to develop the 4-bit bidirectional shift resistor as similar to the normal resistors what we discussed earlier.